I'm going to start the second class, the chemical bonding lecture 2. So in the first lectures, we have shown here the Lewis dot structures, how to draw the Lewis dot structures, and about the some Lewis dot structures. So in these lectures, we will know about the some drawbacks of the octet rule, and also the what is the formal charge. So the formal charge means, so in this lecture we will know about the formal charge. So the formal charge equal to total number of valence electron in the free atom minus total number of non-bonding electrons minus half of total number of bonding electrons. So this is the rules of the formal charge. So the formal charge means, here if you see the total number of valence electron in the free atoms. So we will take the oxygen, so we have to see the how many electrons is present in the valence shell or a neutral state of the oxygen atoms. Then we have to see the total number of non-bonding electrons. So is a oxygen molecule or two molecules, then the how many non-bonding electrons is there. That means that how many electrons are not participating in the bonding. Then we have to see the total number of actually bonding electrons there. So this is the non-bonding electrons. That means this is the non-bonding electrons. This non-bonding electrons means it is a lone pair. So non-bonding electrons means this is the lone pair. Okay. So here in this formal charge, if you see, the everything is number of electrons. There is no pair of electrons. It is also here the number of electrons. They are also the number of electrons, and they are also the bonding electrons. So this is also the all the are actually number of electrons, not the pair. So if I take an example, for example, O3 molecule, this is the ozone. Okay, so first of all, you have to know the structures of O3 molecules. So we know the structures. This is like that. So it will be positive charges and it will be the negative charges. Okay, and so what is happening here? So this is the oxygen is a neutral. So this neutral means it has the two. It has the two lone pair is there. This is the positive charge. Positive charge means that there is deficient of electrons. Okay, so their presence is the two lone pair, and here if you see this is a negative charge, so there is presence of the three lone pairs. So if I mention here, this is the atom 1, this is the oxygen atom 2, and this is the oxygen atom 3, and the question is how you will calculate the formal charge for the every atoms, for atoms 1 and for atoms 2 and for atoms 3. So here now for the atoms 1, if you see the formal charge equal to, so the rules is the total number of valence electrons in the free atoms. So every oxygen atom has the 6 electrons in the valence shell. So this is the 6 minus total number of non-bonding or the lone pairs. So for this atom 1, if you see the lone pair equal to 2. So here the total number of lone pair, total number of non-bonding or the lone pair electrons equal to 2. Then it will be the minus, then it will be the half. Now the total number of the bonding electrons. So if you see this oxygen atom 1, how many bonds is there? This is a 3 bonds, and between among these 3 bonds, 2 bonds is the sigma and 1 bond is the pi. So there is the 3 bond, that means that 3 into 2. So this is the 6 electrons is there. We know that every bond is making by the 2 electrons. So here the bonding electrons equal to 6 because the 3 bond is there, so it equal to 3. So 6. So 6 minus 2 minus 3, so it will be the 1. Now the for atom 2, for atom 2 the formal charge. So every oxygen atoms will have the 6 valence electrons, so it will be 6 minus. Now for the atom 2, if you see the number of the non-bonding electrons, here the lone pair is equal to 3, so 1 2 3, so number of non-bonding electrons equal to 6 minus half. Now how many bonds is there? So this oxygen actually forming the 1 sigma bond. So this is 1 sigma bond means that is the bonding electron 2. So 6 minus 1, so it will be 6 minus 7, that will be the minus 1. So here the formal charge is equal to minus 1, here the formal charge is equal to plus 1. Now the for atom 3, for atoms 3 the formal charge equal to, so we know that total number of valence electrons of an oxygen atom equal to 6, so this will be the 6 minus. Now for the atoms 3, how many lone pairs is present here? There is the 2 lone pair, so non-bonding electrons equal to 4 minus half. Now if you see this atom 3, it is making the 2 bond with this atom oxygen 1. So this 2 bond is 1 sigma, 1 is the pi. So this is the 2 bond, so bonding electron equal to 4, it will be the 4. So 6 minus 4 minus 2 equal to 6 minus 6 equal to 0. So the formal charge, if you see the oxygen atoms 1, the formal charge equal to 1, or oxygen atom 2, the formal charge equal to minus 1, or oxygen atom 3, the formal charge equal to 0. So this is the fact of that every oxygen atom. So there is some point is that there are the formal charge of the each oxygen atoms you can calculate. This is a ozone molecule, this is a O3 molecules. So there is the 3 oxygen atoms are present, so you can only calculate the formal charge of the 3 oxygen atoms, not another, not the molecules. You have to calculate the formal charge of the each atoms. So formal charge means the atoms, the charge of the atoms, not the molecules. So total charge of a molecules cannot be indicated here. By this value of the formal charge of the each atoms, we can calculate the number of the valence electron. So if you see that every oxygen atoms, we can calculate the formal charge. So from that formal charge value, what you can indicate? So from that formal charge value, you can calculate the number of lone pairs, how many lone pairs is present here, or how many non-bonding electrons are present here. Then also you can calculate a number of bonding electrons. So if you calculate the number of bonding electrons, from that you can also calculate the number of bonds, how many bonds are present, how many bonds this oxygen atom actually making with these another atoms, that you can make it. So these are the formal charge, and in this way you have to calculate the formal charge, and from that formal charge value you can calculate it, the number of lone pairs, number of bonding electrons, number of bonds there. So in this previous class we have discussed about the octet rule. Now here we will discuss about some limitations of the octet rule. So we know that every rules has the some limitation, that's why the improvement or the next generations next updated of this rules actually has been made. So every rules has been some the limitations. So here also the some limitations of that octet rule. So first limitations is the incomplete octet of the central atom. So what is that? The incomplete octet of the central atom. So from these lines you have to imagine that there is a molecules. So in these molecules there is the number of atoms are present, but among these atoms there will be a central atoms, but these central atoms will have no 8 electrons in the valence shells. So that means it has the incomplete octet. So what is happening here? If you see the example of, if I taking the some example, suppose LICL. Okay, if you see this LICL, this there is the 2 electrons are present between this lithium and the chlorine. Suppose this lithium here the central atoms. So this lithium is equally, suppose the sharing these the 2 bonding electrons, then it will have the no octet. So in the valence shell there will be no 8 electrons present. So it is the it has the incomplete octet here. So it will the 4 electrons in the valence shell, it will have the 4 electrons, but we are saying that it is stable, and but the center atom has the incomplete octet. So suppose example as BH2. So here the barium is present here. So this is the structures. If you see, this is the bonding electrons. Okay, so this bonding electrons is sharing by this barium also, it is bonding electron sharing by this hydrogen also, but this barium has no 8 electrons in the valence shell. So these are the stable molecules, these are the existed in the natures, in the chemistry, but the point is that without the obey the octet rule, they are the existed. It has the no 8 electrons in the valence shell. So this is the one type of the drawbacks. Suppose the BCl3, trichloroboran. If you see the structures, this will be the trigonal planar structures here. So you know this is the bonding electrons here presence. So these 6 bonding electrons are sharing by this boron, and this the 2 electrons is sharing by also the chlorines. But after that also the boron has to know the 8 electrons in the valence shell. So in this above the molecules, if you see this lithium and the beryllium and the boron have the not the 8 electrons. So to be the 8 electrons, at least the atoms should have the 4 valence electron. Some other such the LCl3 and the BF3 molecules also is there. They are the not the following the 8 electrons in the valence shell. So another the limitations of that octet rule is the odd electron molecules. Odd electrons molecules. So this odd electron molecules is that if you see the some example, suppose the NO. So the structures is N double bond O here. So this oxygen, so nitrogen has the 3 lone pair, and oxygen has the 4 lone pair electrons. So 2 lone pair is there. So if you see this the Lewis dot structures, this oxygen atom is there and there. So it has the 3 lone pairs. It has the 2 lone pairs. So these nitrogen atoms, if you see this valence shell of this number of electrons in this nitrogen atom, 4, 5, 6, 7. So 7 electrons is there. But for this oxygen atom, 1, 2, 3, 4, 5, 6, 7. So it's 8 electrons is there. So here the oxygen atoms actually following this octet rule. It has the even electrons in the valence shell. But for that nitrogens, if you see this 7 electrons, so it is the odd electrons. So this is the odd electrons is present in the valence shell. So this is a one type of the drawback where the odd electrons are present in the valence shell. After that also it is the existed. So another example, if you see NO2. So N double bond O, here this is a O positive, this is a nitrogen positive, the oxygen minus. So this is the neutral, so oxygen has the 2 lone pairs, and this is the one positive charge is there, that means these 2 electrons are gone. So one's lone pair is there, or 1 electron is there, and there is the 3 lone pairs. So if you see the Lewis-Dot structures, if I draw the Lewis-Dot structure, so what will be happened here? So this will be the bondings, and that will be also the bonding case. So it will be the bonding here, and there is the 2 bond is there. Okay, so this is will be that. So if you see this nitrogen atom, for that nitrogen atoms, so there is the 1 electron. So total number of the valence electron equal to 1, 2, 3, 4, 5, 6, 7. Here also the 7 electrons is present. So it is the odd electrons. So in these 2 examples, you can see that in the valence shell there is the odd electrons are present, not the 8 electrons, not the even electrons. Okay, so after that also it existed. So this is the one type of the limitations of the octet rule. Then the another limitations of the octet rule is the expanded octet. Expanded octet, that means that there will be a number of electrons greater than the 8 electrons. Okay, so how many electrons will be present for the octet rule? It is the rule is that the 8 electrons will be the present. But for that expanded octet, here the number of electrons will be the greater than more than the 8 electrons. Okay. After that also they are the stables. So for example, if you tell me, if you see the PF5, SF6 and H2SO4. Okay. Here if you see that every central atoms has valence number of the valence electrons in these molecules. Every sulfur atoms and phosphorus atoms is the central atoms. So these central atoms has the number of valence electrons greater than and more than the 8 electrons. So this is called the expanded octet. So greater than 8 electrons, presents the number of electrons is greater than 8 electrons. After that also these are the stables and the existing natures. So this is also the one types of the drawback. If I draw the structures for that PF5 molecule, so the structures will be the trigonal bipyramidal structure. So it will be the TB structures. So it will be the fluorine here. Okay. So if you see the nitrogen phosphorus is there. So every bonding electrons is present here. Okay. So if you see this, every bonding electrons is sharing by phosphorus also. So number of bonds equal to the 5. So 5 into 2 is equal to 10 electrons. So in the valence shells, the 10 electrons is present. It is obviously the greater than the 8 electrons. So it is the avoiding the octet rule, but after that it is the stable. So this is the one type of the limitations of the octet rule. If you see the SF6, we know that structures of the SF6 equal to octahedral. So this is the fluorine, this is the fluorine, this is the fluorine, this is the fluorine. Here if you see the 6 bond is present. So 6 into 2 equal to 12 electrons. So in this valence shell of the sulfur, the 12 electrons are the present. That is the greater than the 8 electrons. So it is the expanded octet rule. So this is called, it is called the expanded octet rule. Okay. So these the 3 are the limitations of the octet rules. After that also they are the stabilized. So there are also other the drawbacks of the octet rule is that there is some other drawbacks. If I write here, the octet rule based upon the chemical inertness of the noble gases, based upon also combine with oxygen and the fluorine to form number of compound like HCF2, trifluorochromium, HCOF2. So these are the actually, so this drawback is saying that we know that the noble gases has the inert these are the noble gases which are the inert because it has the 8 electrons already in the valence shell. So when it has the 8 electrons in the valence shell, so these are the inert gas, these are the inert. So they are not capable to react with these other molecules. But here also we are seeing that the noble gases such that the xenon and the chromiums, they are making the compounds with this oxygen and the fluorine. So then in the octet rules, it is saying that if the every atoms, if the in the one the atoms has the 8 electrons in the valence shell, so it is the inert. So this is the not the true proposals here, because we know that the xenon also is a noble gas. It has the 8 electrons in the valence shell. After that also it is a makings with the some molecules is here. So this is the one type of the drawbacks here. The second drawbacks, if you see that this theory does not account for the shape of the molecules, because from that octet rule just we can calculate it the how many electrons present in the valence shell, and we can say it is stable or the it is not stable, but it is existed or the not existed in the natures, but we cannot say the shape of the molecules. So it does not account for the shape of molecules. Second thing, if you see, it does not explain the relative stability of the molecules, or it cannot say the proper, it does not gives proper explanation of the stability of a molecule. So these are the some drawbacks. Here we can say there are the some drawbacks which is the very important, that the expanded octet rules and the odd electrons, the molecules, and the incomplete octet of the central atom. So these the three drawbacks are the very important. After that there is the three drawbacks which is also important, that it does not give the any shape of the molecule, does not give the any proper explanations for the stability of molecules, and also we know that for that xenon case. So these are the drawbacks. Now after that we will know about that ionic and the covalent electrovalent bond, how this ionic bond and the electrovalent bonds are the making. So here I am taking say general example, general equations. So if I see this the metal M, so this is the ionized here, so that means that it is the giving the 1 electrons, so M plus these electrons. So this is the ionization enthalpy. So whatever electrons they are giving out from this metals, suppose that is the sodium, the sodiums is the forming the sodium plus and the giving the 1 electron. So with the releasing the 1 electron, it is the forming these cations. So this is the ionization enthalpy, and here this is the halide. Suppose there it is taking this 1 electrons from this another source or from this here, and it is the forming is the 1 anions. So it is a gain. So here the electrons is the gaining. So this is called the electron gain enthalpy. Electron gain enthalpy. So what is happening if I sum up these two equations? So M and the X, this is the sodium, suppose this is the sodium and this is the Cl. So NaCl is forming, but it is the ionized as a M plus gas. So these electrons are the cancelled here, and also the forming this is the X minus. So there is the 2 electrons, so there is the 2 factors, one is the ionization enthalpy, another is the electron gain enthalpy. These two ionization enthalpy is happen when this it is ionized, that means the 1 electron is the releasing, but electron gain enthalpy it is the 1 electron is the gaining. So for that ionic bond or for the electrovalent bond, there is a statement is that first statement is ionization enthalpy is always endothermic, that means it will be the positive endothermic process. That means that we have to give some amount of the energy to release this electron from the metal center. Okay, that is called the ionization enthalpy. Okay, so that's why it is an endothermic process. Second is the electron gain enthalpy. It is not sure. It will be the maybe the exothermic process. Some processes, some examples is there. It is the exothermic, and some example is there. It is the endothermic. So for that ionization enthalpy, it is fixed. It is always the endothermic process. Some amount of the energy is needed to release these electrons. But the electron gain enthalpy, it could be the exothermic process, it could be the endothermic process. So the low value of the ionization enthalpy and the higher negative value of the electron gain enthalpy favors to forms a ionic bond. So there is a comment is that low value of ionization enthalpy and a higher negative value of electron gain enthalpy favors to forms a ionic bond easily. So to forms a ionic bond, this ionization enthalpy value, this enthalpy value should be the low, and this so it will be the positive value, but it will be the very low positive value. But the electron gain enthalpy, it will be always the higher the negative value. It will be the very so overall the negative value will be gives. So we will get the delta G equal to the negative. So that's why the ionic bonds will be made for that case. If you see, for example, NaCl. So in the 3D arrangement of the cations and the anions, if you see the structures of the crystal structure of NaCl is rock solid, rock salt. So it is a cubic structures. If I draw here, this is like that actually. So this is the drawing this fact is that, so this is the complete structures here. So here it is the Cl minus. Suppose it is the Cl minus, it will be the sodium plus. It will be the sodium plus, and alternatively this every cations and the sodium and the Cls will be present here. So this is the rock salt structures. So in this ionic salt, the sum of the electrons gain enthalpy and the ionization enthalpy may be the positive, but due to the release of the energy of the formation of this crystal lattice, it will be the stabilized. What is happening here? So in these structures, if you see, the sodium is forming the sodium plus, and this one electron is here. This Cl is taking these electrons and it is the forming this Cl minus. Okay, so here the ionization enthalpy. So here the ionization enthalpy is 495.8 kilojoule per mole, and here the electron gain enthalpy equal to minus 348.7 kilojoule per mole. So if I sum it, so 147.1 kilojoule per mole. So it is the giving the positive value. So after that also it is the stabilized, because in the ionic salt, the sum of the electron gain enthalpy, here if you see, the sum of the electron gain enthalpy is the negative, but sum of the ionization enthalpy it also the positive, but this positive value is the very high. If I sum this ionization enthalpy and the electron gain enthalpy, it is the giving the positive, but due to the release of the lattice due to the release of the energy of the formation of the crystal lattice, due to the release of energy of formations of the crystal lattice, it is stabilized. So the enthalpy of the formation of the NaCl lattice equal to, if you see, so it is stabilized. So the enthalpy of the formation of the NaCl lattice is equal to minus 78 kilojoule per mole. That's why initial is the stable in. That's why initial is stable in ionic form. So that's why it is the stabilized, because this total enthalpy, if you see this formation, because this lattice energy is there and the lattice is forming, then some amount of the energy is also the releasing. So if you sum of that, so the formations of that lattice equal to minus 78 minus 788 kilojoule per mole. So it is a high negative value. So that's why it is a stabilized. So here I will stop these lectures, and so in these lectures we have taught about the drawbacks of the octet rules and the formal charge, and the how this ionic bond is forming, and what is the conditions to stabilize these compounds in this ionic form. So in this next class, next lectures, we will know about this another the topic. So here I am going to stop this lecture.